Hi, my name is Will Summers, and this is my video for the Test 2 wrapper for the second midterm of this fall. The point of this wrapper is to describe a problem that we had most trouble with in the exam and explain it to our fellow classmates so they could use it as a learning technique. The problem I chose was problem none. Problem number one, using the energy principle. Uh, for this problem, we were given a structure of four different masses, length with a radius in a circular form with a radius r apart. These four masses are moving in a circular motion around each other, and because of gravitational principle. And what we have to do is calculate how long the system takes to make one complete revolution. We're going to start with the energy principle right here. This energy equals work times Q. We know there's no Q, and we know that work is 0 too because there's no displacement. Moving on from that, we know that energy is equal to change in K plus change in U. And we know that our total energy is 0, so K must be equal to U. Moving on, we can see that K, because it's in a circle, is equal to mv squared over r, and that our potential energy, or gravity potential energy, is equal to the gravity principle, which is the gravitational constant G times mass 1 times mass 2 squared over the distance squared. However, there are three different distances. The first, so each of the three different m's, the long one is 2r and the two short ones are r root 2. So we have to split up the gravitational principle to what we see there and then set them equal to each other. And moving on, as we simplify more, we get what we have there, and then we solve for v. And we get this final answer. V equals the square root of r times negative gm squared over 4r squared times negative g over r squared times m. However, we're not solving for v as our final answer. We're solving for time. We know that velocity equals distance over time, and time equals distance over velocity. The total distance that we travel is our circumference, our 2 pi r, as we get right here. And if we know that time is equal to 2 pi r over the velocity, we can get our final answer just by putting 2 pi r over velocity. And for the second part of the problem, what we had to do is label the force acting on each particle A and particle B with direction and somewhat magnitude. While taking this in the test, I was a little confused. I thought that we'd have to break it up in parallel and perpendicular components, and the force would be between that. However, as we saw in the online lecture videos, the force is always in the center of motion because of the kissing circle, as it was labeled. So this problem is actually much easier, and we could see, although the picture is sideways, that the force is towards the center of its motion. Thank you.